All right, we'll go ahead and get started here. Thanks everyone for coming virtually this week for our seminar. We have Dr. Lu here today from Norway as of right now, um, coming to talk to us today about her research on supervised learning for multiple disease screening and all of the advancements that she's been able to make in the field. I'll give the rest of the time to you, Dr. Liu. It's a full 50 minutes plus time at the end for questions.
Okay, thank you so much for the introduction, Annan. So, good afternoon, everyone. So now I'm in Norway, and today I'm very honored to share my research with you. So my talk is about partially supervised learning for multiple disease screening. And to begin, so I would like to share you some statistics of the retinal diseases. So, according to the survey by the Prevalent Blindness of America, and this survey found that the blindness is the third most feared health concern, followed the cancer and the heart disease. And the five leading causes of the blindness are the cataract, the glaucoma, and the refraction error, and age-related macular degeneration, and diabetic retinopathy, and the retinal diseases. The retinal diseases affect a very large number of people worldwide. For example, there are around 80 million people worldwide suffering from the glaucoma, while there are around 196 millions suffering from the age-related macular degeneration, and around 103 million people suffering from the diabetic retinopathy. And in practice, and the ophthalmologist capture the fundus or photography from the patient, and then with these fundus images, the ophthalmologist assess the condition of the retina. For example, they look for the abnormalities from the fundus, and they check whether there are lesions on the retinal fundus, and if there are lesions on the retinal fundus, and then what kind of the lesions are, and how many lesions are there, and where are the lesions are located, and also, and whether there are the other like the retinal disease symptoms. And according to these findings, and the ophthalmologist make diagnosis decisions. For example, whether the patient is suffering from the diabetic retinopathy, or whether the patient is suffering from the glaucoma or the age macular degeneration, or the person is in a health condition. However, the large-scale screening for the millions of people is not always feasible in many countries. For example, particularly in the low-income countries, due to the limited eye care services and the heavy workload on the ophthalmologists. So to make the eye health care services be more accessible to more people, and to reduce the workload of the ophthalmologist, we need to develop AI-powered automated retinal image reading system to classify the retinal diseases. And um, and to and during the past 2 decades, there are many research about screening single retinal diseases, and these methods are very promising. However, in the real clinical applications, we need to simultaneously identify the multiple retinal diseases. We need to identify as many diseases as possible. So we need to develop the multiple retinal disease screening system. And to do this, there are two key elements. One is the data, and the other one is the machine learning algorithms. And let's first look at the data and see what kind of the data we can use. So if we take the retinal disease as an example, and here we list several publicly available data sets which were collected for the retinal disease classification. And from this table, we can see we can use many publicly available data sets to train the retinal diseases. And however, this is the only one data set which provide the labels for these 6 retinal diseases and the normal condition. While for these data sets, for these 1, 2, 3, 4, 5, for these 6 data sets, they only provide either like here 3 labels for 3 for 2 diseases and the normal condition, or only the label and the label for only a single disease. And for example, here the DDR dataset only provides labels for diabetic retinopathy, where this dataset Refugee 2 only provides labels for glaucoma. And for this dataset, ADAM only provides labels for age-related macular degeneration. So, and with this dataset, we can use like the fully supervised learning way to train. And from this table, we can observe that most of the data sets have the problem of label missing, and each data set was collected from a medical data set, and thus this data set were collected from multiple domains. And to train a multiple retinal disease screening model, and we can use the fully supervised learning way. We can use the fully supervised learning way. And on this dataset, because this dataset ODIR provides labels for all the these retinal diseases, and also for labels for the normal condition. And however, this dataset is a small scale dataset. And also, the fully supervised learning method assumes that the test samples and the training samples were collected from the same medical set and follow the same data distribution. So if the test sample is from the same medical set and follows the same distribution as the training sample, and then the disease classification performances are usually excellent. However, if the test sample is from a different medical set and follows a different data distribution to the training samples, and then the disease classification performances usually decrease dramatically. And the second option is to leverage the foundation models. Because recently the foundation models have attracted a lot of attention from the community. And the foundation models are usually trained with very large scale pairs, where each foundation image is associated with text descriptions. And leveraging this adaptability of the foundation model, we can perform zero-shot inference. for the multiple retinal disease classification. And however, the zero shot inference performances are not always are not satisfying. And the reason is straightforward and obvious because we do not use this strong supervision signal to train the model, and the text supervision is too weak. And for these two kinds of the learning paradigms, and we can see that they do not make full use of the data, the information we really have. And basically, for the fully supervised learning method, and they directly throw away the training samples which are not fully annotated. And for the zero-shot inference method, and they do not use the information of the ground truth. And then we started asking a question here, and can we make full use of the data for training? And the answer is absolutely yes. And this comes to another question. And how can we make full use of these images and the partial labels to train such a screening model to classify multiple retinal diseases? And this is the question in I want to answer in what follows. So we propose the partially supervised learning paradigm to solve to answer this question. And let's again look at the data we do have. And as we mentioned before, and the data we can access are partially labeled. And the training samples are from from multiple domains, and they follow different distributions. And thus we need to solve two challenges. The first challenge is the label missing challenge, and the second challenge is the multiple domain. This means that we need to deal with the domain shift problem. And to solve the label missing problem, we propose the self-training framework. And this framework consists of two branches. And here, the first branch is the deterministic future learning branch. And this branch takes the input image as takes the retinal images as input, and learns the deterministic future maps. And with these maps, we can do the classification and get the pseudo labels for the unknown classes. And the second branch is here, the probabilistic future extraction branch. And this branch is supervised with the pseudo labels from the deterministic future extraction branch and the ground truth of the known classes. And and the second branch here, the probabilistic future learning branch, is designed to learn the domain invariant futures, and through the knowledge distillation, and through the knowledge distillation, and we can distill the knowledge of the domain invariance from the probabilistic future learning branch to the deterministic future learning branch. And in this way, and we can enhance the performances of the deterministic future extraction branch. Then let's see how the deterministic future learning branch works. And first, with here the a mini batch of the retinal images X1, X2, and XB, and we put we feed these retinal images uh, to a encoding to a image encoder, and usually this image encoder can be like the CNN, such as the resonant or the convolutional, and also the image encoder can also be the visual vision transformer like Swing, and then we can get the future maps, and we denote the future maps as the F1, F2, and FB here. And then we decouple the future maps to diseases wise futures guided by the text descriptions of the disease symptoms. And so here, for each disease, for example, for the glaucoma, and it has some symptoms. For example, the symptoms like the optical nerve abnormalities and the abnormal size of the optical curve, or the anomalous size in the optical disc. And with these symptoms about the glaucoma, and we put these text descriptions into a bioclinical bot, into a large language model, and this large language model is pre-trained with the clinical nurse, and then we can get the text embeddings about the disease symptoms. As here, for each disease, we have several symptoms, and we directly average over the text embeddings of the disease symptoms, and then we can get the disease-wise features. Suppose we want to classify for T diseases, and then we can get T diseases with text embeddings. We denote these disease text embeddings as D1, D2, and D capture T here. And also for the visual features extracted from the images, and we calculate the attention score of each of future vector at each location, and the disease-wise features through this equation. And with the attention score, and then we can directly use the attention score as the weight weighted average over the visual features, and then we can get the disease-wise features. And here, the circled dot is the product, and here WF and WT two weight matrices, and these two weight matrices project the vector project here the future vectors, and here V is also a nullable vector. After we get the disease-wise features, and then we can directly do the classification using the very simple linear layer, and then we can get the predictions. With the predictions, we use the cross entropy over the num classes to motivate the num of this branch. And here with the predictions, and for the unknown classes, we can simply use the thresholding strategy to assign pseudo labels for them. Specifically, if this network can confidently make predictions for the unknown classes, if the probability for unknown for unknown class T is greater than a threshold tau, and then we assign a positive label to this unknown class. And if the probability of for the unknown classes for the unknown class is less than a threshold 1 minus t, and then we assign the negative label to this unknown class. And so far, we know how the deterministic future learning branch works and how to get the pseudo labels for the unknown classes. And then let's see how the probabilistic future learning branch works, and how to inject the uncertainty to this probabilistic future learning branch to boost the domain invariant of the futures. So basically, we propose the domain shift the uncertainty block, and we insert these uncertainty blocks into each stage of this backbone of this network. And so here we can see the probabilistic future learning branch share the same weight, share the same architectures of the deterministic future learning branch, and it is incorporated with the uncertainty blocks. And here, basically, for the futures for the future maps output by the encoding block, and we estimate the mean and the variance of these future maps output by the encoding block. And we use the mean and the variance to characterize the domain characteristics. And then we assume here the mean and the variance follow the Gaussian distribution, and within each mini batch, and then we can estimate the parameters of the Gaussian distribution. And then we can estimate two distributions, and one distribution is about the distribution of the mean, and the other one is about the distribution of the variance. And with these two distributions, and then we can randomly sample a new mean and a new variance, and then we can randomly generate the future maps. And we term the randomly generated future maps as the probabilistic future maps. And similar to the deterministic future extraction branch, and we feed these probabilistic future maps to the texture guided semantic decoupling to get the probabilistic disease-wise futures, and then we can do the classification, and then we can get the prediction for both the known classes and the unknown classes. And then we distill the knowledge known by the probabilistic future branch to the deterministic future branch. And here we use both the future distillation, and the output level knowledge distillation to transfer the knowledge for the future level knowledge distillation, and we directly minimize the maximum discrepancy loss of the futures of the futures by the probabilistic future learning branch, and the futures by the deterministic future extraction branch. And for the output layer knowledge distillation, we directly minimize the KL divergence between the norm classes predicted by the probabilistic future learning branch and the norm classes predicted by the deterministic future learning branch. And to validate the effectiveness of our partially supervised learning method, and we combine 6 data sets as a metadata set. So here and here, the first data set, cargo cat, provides labels for the normal condition and for glaucoma and for cataract. And here, the DDR dataset provides labels for the diabetic retinopathy, and the refugee 2 dataset provides labels for glaucoma, and this dataset provides labels for here the age, the AMD, the age macular degeneration, and this dataset provides labels for the retinal hypertension, and this dataset provides labels for the pathology myopia. So basically, we can get the we can use the labels for these 6 diseases and also the label for the normal condition from these 6 data sets to train a model to classify the diseases and also identify the normal condition. And here we also use this 4 data set. And the test of this data set can be used to validate the in-domain performances of our method. And here for the 4 data set. So here for the 4 data set here, and we use them to evaluate the out of distribution performances, and also here for all the IR and all the IR 200/3, we validate the out of domain performances on these 2 data sets. And here we show the performances of our method, the PS screen, and also the performances by 5 partially supervised learning method, and also here 2 baseline methods, Martinet and Marti-Hess, and here the full supervised learning full supervised learning method on all the IR dataset. So here the Martinez, this method trains multiple disease specific models on the metadata set. And for this baseline method, we share the backbone where we attach different classifiers for each specific retinal disease, and then we only use the labels for norm classes to train this Marti-Hess model. And from this table, we can see basically our PS screen method can achieve better performances than the baseline methods, as well as the compiled of 5 state-of-the-art. And also on the SIM dataset and on this ODIR dataset, and our method achieve superior performances to the compiled methods, and to show to show that our partially supervised learning method employed the discriminative information from the abnormality regions. We use the grade CNM method to get the heat maps from the last convolution layers. And here we can see that for the age macular degeneration diseases, and our method can correctly localize the hemorrhage here, and also can localize the exodus. And while the baseline method Marty has couldn't correctly localize the abnormal regions. And also here for glaucoma, and our method can localize the optic disc and the cap region, while the baseline methods localize the background of the retina images. And here is the examples for the pathology myopia, and here are the retinal atrophy. So here are the retinal atrophy regions, while the baseline methods wrongly localize the retinal atrophy regions, while our method can correctly localize here the retinal atrophy regions. And also we compare our partially supervised learning method with the zero-shot inference with foundation models, and to show that fully making use of the data information works better. To train the model outperforms the models which do not use fully use of the data, the image and the labels. So here we compare our partial supervised learning method with three foundation models. And these three foundation models are CLIP and Biomet CLIP and FLAIR. And from these three foundation models, CLIP is pre-trained with the natural images and the descriptions. And here Biomed CLIP is pre-trained with the medical images and the descriptions of the medical images, while FLAIR is a foundation model pre-trained with the retinal fundus images. And from this figure, we can see that our partially supervised learning method can significantly outperform the zero-shot inference with the foundation models. And also the reason is also very straightforward, because these three models do not utilize the ground truth labels for the diseases. So the capability of the zero-shot inference for unseen diseases of our proposed partially supervised screening model remains to be investigated. And we also validate the effectiveness of our proposed partially supervised method with on the chest X-ray image classification task. And here we train the model on the chest export, and this dataset contains partially labeled X-ray images and covering of 14 classes. And then we do the in-domain validation on the test of this dataset. on the test of this data set. And also we evaluate the out-of-domain performances on these two data sets. And from this table, and we can see for the in-domain performances, our proposed method can achieve the best performances. While on this data set, our method achieve the second best. And on this data set, our method also achieves the best performances. And this means that the partially supervised learning method can also be applied to the other health domains. So here I would like to deliver some take-home messages. So basically, the partially supervised learning method can fully utilize both the images and the labels from multiple data sets and to train a universal disease screening model. And the partially supervised learning method can achieve a very good performance in screening the retinal diseases and can achieve a very good generalization capability to out of distribution samples. And also this method can be applied to the other health domain, such as the chest X-ray image classification. And after this work has been accepted by last year's BMVC, and we still thought about a question is that can we model the multiple domains in a more explicit way? And to answer this question, and we are inspired by the factor of the factor. We are inspired by the factor and that the low frequency components usually represent the low-level statistics like the brightness and the color distributions. And so usually we treat the low-frequency components as domain-related. If we perturb the low-frequency components, and then we can enhance the domain invariant of the features. And basically, and for the high frequency components, and is always they always associated with the edges and the boundaries of the structures, such as the tiny lesions and the anatomic structures, such as the vessels or the boundaries of the optic disc and the optical cap. So these high frequency components are usually disease related and domain invariant. So when we do the when we perturb the images, so we need to maintain the high frequency components and to encourage the network learn the intrinsic and the disease related features for screening. And to do this, we propose that we extend the previous method and propose to augment features in the frequency domain. So in the second version of our partially supervised learning method, we propose to perform the augmentation to inject the uncertainty in the frequency domain. So we propose this method. So this method consists of 3 branches. So here is the teacher branch. This branch is completely same with the branch in the PS screen V1, and to enhance the domain invariant of the features. So here we propose the low frequency dropout and the adversarial low frequency uncertainty branch. And so basically, so the teacher branch is completely same with the deterministic future learning branch in the first version. And here for the for the student one branch. So we so here for the future maps in the spatial domain, and we use the Fourier transform to transform the future maps into the frequency domain, and then we drop out the low frequency component randomly, and then we use the inverse of Fourier transform to get the future maps. And then similarly, we attach the text-guided semantic decoupling modular to get the disease-wise futures, and then we can do the classifier. And here we use the pseudo labels generated by the teacher branch to supervise the learning of this branch. And here for this branch, and for the second student branch, and we perform the uncertainty in the frequency domain. And so similarly, we use the Fourier transform to get the frequency of the future maps, and then we get here we estimate the statistics of the low frequency component. Here we get the mean and the variance of the low frequency component, and then we inject the random noises to these low frequency statistics of the low frequency component, and then we can get here the random mean the new mean and the new variance, and with here the noise the mean and the noise the variance, and then we can get the and we can and then we can get the random futures, the augmented low frequency components in this way. So here is the scale of operation, and here is the shift operation, and then we can perform the inverse Fourier transform to get the augmented futures, and to name and for this branch, and we use the cross entropy loss for the norm classes, and we also use here the pseudo labels of the unknown classes to supervise the learning of this branch. And basically, here we use the adversarial learning to learn here the parameters of the Gaussian distribution. And in this way, we know how large the noise we can inject to this branch. So here are the performances of this method, the PS V2, and on the metadata set. And from this table, we can see and the performing argumentation in the future in the frequency domain, and then we can get better performances on here on the metadata set, and also we can get better performances on SIM dataset and the ODIR dataset. This means that the second version of our partially supervised learning method can perform better performances on the in-domain dataset as well as the out-of-domain dataset. And also, it can perform better performances on this dataset compared to the zero-shot inference performances with the foundation models, as well as here the first version. And also here we show the results on the chest X-ray image classification task. And with the argumentation strategies in the frequency domain, and then we can see here on this dataset, the performances are significantly improved. So, uh, in uh, in summary, and we can conclude that the learning-based domain uncertainty is beneficial for models' generalization capability, and our partially supervised learning method can be applicable to different health domain. So I would like to thank all of the co-authors of this two work, um, and Bo Yi, my PhD student, and Professor Yanin Zheng from the University of Liverpool, and Professor Hu Walio from the Medical University of Vienna. And also, this work is supported by the Research Council of Finland and also the CSC computational platform. And here are the QR code for these two papers and the course for these two work. So if you have interest, you can refer to the papers, and also you can try our course. And that's all my talk.
Thank you very much. Does anyone have any questions for Dr. Liu? I just have a real quick one. Have you looked at this kind of modeling in other different types of diseases that are not just based on eye diseases? Any other kind of diseases that you've been able to look into?
Uh, yes, and we validate the effectiveness of our proposed methods, and also the chest X-ray images to classify the chest X-ray diseases.
Okay.
Yes.
Are there any other questions for Dr. Liu?
No, thank you.
Thank you.
All right, with that, if you are in here with B601, next week we'll have Landon Tier be in person for his PhD update. I give you a lot of thanks, Dr. Liu, for taking time out of your schedule to come talk to us. And like I said, this seminar is recorded and everybody has those QR codes that Dr. Liu shared. So if you have any questions, feel free to reach out to Dr. Liu. Other than that, everyone have a nice day.
Thank you. Oh, by the way, we are
Yes.
recruiting. Yes, we have two vacant positions. One is the research assistant, and the other one is the postdoc researcher position. If you have interest, so please contact me by email.
Yes, I'll share that information too. So if anyone wants to leave Louisville and go international, feel free to reach out to Dr. Liu.
Many thanks.
Thank you very much. Have a good day.
Thank you. Have a good day. Bye bye.
Bye.